Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my M.Sc Analytical Chemistry class. I am Dr. S.R. Labhade, working as Associate Professor in the Department of Chemistry at College, Nashik. Student, in today's lecture, we discuss some qualitative and quantitative applications of stripping voltammetry. In previous lecture, we discussed the analysis steps involved in stripping voltammetry. There are two steps. First step is called as concentration step and second step is called as stripping step. In addition to this, we discuss the working of anodic stripping voltammetry as well as working of cathodic stripping voltammetry. We also discuss why there is need of a cathodic voltammetry, cathodic stripping voltammetry, and applications anodic stripping voltammetry. Student, in today's lecture we discuss the different applications of stripping voltammetry. Stripping voltammetry is a two-step electroanalytical technique. In first step, that is called as concentration step, the analyte is electrolytically deposited onto the working electrode. During this, a time is measured and this deposition may be carried out by stirring the solution. Therefore, very small amount of the analyte get deposited onto the working electrode. In second case, the potential is linearly scanned in opposite direction and a stripping, that is removal of analyte, is carried out from the working electrode. That step is called as stripping step. In a stripping step, the potential at which we observe the current is called as peak potential, and the magnitude of current at that potential tells us what is the analyte and how much it is. That means both qualitative as well as quantitative analysis is done by stripping voltammetry. Therefore, qualitative analysis in stripping voltammetry is done. Qualitative analysis in stripping voltammetry is done by using a peak potential, which is called as EP. Peak potential is the oxidation potential when we dealing with anodic stripping voltammetry, or peak potential is the reduction potential of the analyte when we are performing cathodic stripping voltammetry. Therefore, here in anodic stripping voltammetry, analyte is removed by means of oxidation process, during which the oxidation potential is the identity of the material, and in cathodic stripping voltammetry, analyte is removed from working electrode by reduction process and cathodic current is measured. Therefore, reduction potential in cathodic stripping voltammetry and oxidation potential in anodic stripping voltammetry are useful for identification of the analyte species which is stripped from the electrode. From the working electrode. Student, now we discuss the quantitative applications of stripping voltammetry. Stripping voltammetry is useful for determination of trace concentration of metallic ion species. Quantitative applications of stripping voltammetry. First application, simultaneous determination of copper and cadmium by anodic stripping voltammetry. If sample solution containing two or more depositive species, those differs widely in their reduction potential, those can be simultaneously determined by stripping voltammetry. Now we discuss the applications of anodic stripping voltammetry in determination of copper and a cadmium from the mixture. Copper, that is oxidized at potential minus 0.2 volt, while cadmium is oxidized at potential minus 0.6 volt. Therefore, the oxidation potential of these both species differs widely, and therefore we can easily determine copper and cadmium from the mixture. Therefore, initially the concentration state is carried out at potential minus 1.0 volt versus saturated candle electrode with stirring solution. So that at this potential both copper 2 plus and cadmium 2 plus are get reduced to copper and cadmium metal or amalgam. That means when a working electrode is a mercury. Therefore, here in stripping state, the potential is linearly scanned to positive direction at potential. When it reaches to minus 0.6 volt, then a peak current for cadmium is observed, and at minus 0.2 volt the peak current of copper is observed. The voltammogram or stripping voltammogram is like this. Here current in microampere versus EMF in volt. We have two peaks. One at here minus 0.6 volt, second at minus 0.2 volt. This is for a copper, this is for a cadmium. The area under the curve or the peak current current is directly proportional to the concentration of ions in this solution. In this way, we can determine simultaneously copper and zinc in the mixture by analytic stripping voltammetry. Initially, potential is kept minus 0.1.0 volt so that copper as well as cadmium get concentrated onto the mercury top. Then potential is scanning opposite direction. When it reaches to minus 0.6 volt, a peak current for cadmium is observed, and when it reaches to minus 0.2 volt, the peak current for copper is observed. The peak current directly proportional to the amount of material or amount of copper and cadmium present in this solution. Similar experiment is performed for a standard solution of copper and cadmium for determination of copper and cadmium in the sample. Now we discuss the second application, that is a determination of copper, cadmium and zinc by pulsating anodic stripping voltammetry. Here we discuss the application of determination of copper and zinc. Now we have to discuss the determination of copper, cadmium and zinc in the mixture by pulsating anodic stripping voltammetry. Now in this case, concentration step is carried out at potential minus 1.2 volt versus saturated carbonate electrode with stirring the solution, so that all metal ions including zinc are get deposited. Therefore, all copper, cadmium and zinc get deposited. In stripping step, potential scan is not linear, it is in a pulsating mode. That means initially potential is directly reduced to minus 1.0 volt versus saturated carbon electrode, so that we observe a zinc peak current without linear scanning. Here potential is directly scanned to minus 1.0 volt, where a oxidation current for zinc is observed. Then potential is directly reduced to minus 0.6 volt, so that a cadmium peak is observed. And third case, potential is directly reduced to minus 0.2 volt versus saturated carbon electrode, so that a peak current for copper is observed. And these peak currents are directly proportional to concentration of copper, cadmium and zinc in the mixture. For quantitative analysis, same experiment is performed with a standard solution of zinc, copper and cadmium in a mixture. In this way, a pulsating anodic stripping voltammetry, in which without linear scan we can scan potential in a pulsating matter, so that we can observe those peak at that respective oxidation potential or reduction potential. By pulsating method we can increase the sensitivity, because the interfering ions, their interference can be removed in a pulsating mode. Student, now we discuss the applications of anodic stripping a different metal ions present in the mixture. Third application, that is a simultaneous determination of bismuth, copper, lead, cadmium and zinc in the seawater. Therefore, simultaneous determination of these different cations is possible by a anodic stripping voltammetry. Therefore, in this case, the concentration step with sample as well as standard is carried out at a potential minus 1.4 volt versus saturated cadmium electrode with stirring the solution so that all the metal ions are get concentrated onto the mercury drop or a working electrode. Then stripping step is carried out either by linear mode or in a pulsating mode. When potential reaches equal to minus 1.0 volt versus saturated cadmium electrode, we have peak current for zinc. Therefore, we have IP for a zinc. When potential reaches equal to minus 0.8 volt versus saturated cadmium electrode, not 0.8, 0.6 volt, then we have a peak for a cadmium. When it reaches to minus 0.4 volt, then we have a peak current for lead. Similarly, at potential minus 0.2 volt, we have a peak current for a copper. And at potential minus 1.0 volt, we have a peak we have peak current for a bismuth. That means here, these zinc, cadmium, lead, copper and bismuth differs widely in their oxidation or reduction potential, and therefore simultaneous determination of this metal ion is possible in a single analytical run by means of anodic stripping voltammetry. For quantitative purpose, same experiment containing a standard solution of copper, cadmium, lead and bismuth, zinc in a mixture, and the peak current obtained with standard are matched for the sample for quantitative determination of ion present in the sample. In this way, we can measure more than 5 elements by this stripping voltammetry if those are differs widely in their reduction potential. Now we discuss the next application of this stripping voltammetry, that is determination of lead in blood sample. We know that lead that will be reduced or oxidized at potential minus 0.4 volt versus saturated cadmium electrode. Therefore, we can determine trace concentration of lead in blood sample by means of a stripping voltammetry. Lead that is concentrated in the blood of industrial workers as well as in the blood of traffic police. Tetraethyl lead and tetramethyl lead are used as an anti-knocking reagent in a petroleum product, and lead oxide particles are given out from the exhaust of the vehicle. These are get inhaled by the persons which are continuously in contact with this exhaust. Therefore, lead concentration in the blood is getting increased. When concentration of lead in the blood is increased, that affects the functioning of hemoglobin. The functioning of hemoglobin is to transport the oxygen from lungs to the body part. Therefore, interference of lead will be present with this transportation, and therefore it is essential to determine the trace amount of lead in the blood sample. The procedure for this purpose: a blood sample, a known blood volume of 0.2 to 0.5 ml is digested with a perchloric acid and a nitric acid, so that all organic matter in the blood is removed. The solution is then diluted and analyzed by the stripping voltammetry. Then concentration step for standard solution of lead and standard sample solution of lead is carried out at minus 0.6 volt versus saturated cadmium electrode. And stripping step, that is pulsating or sometimes a linear stripping. The peak current observed at 0.401 volt versus saturated cadmium electrode is the peak current for a lead ion. Therefore, here peak current for sample and peak current of standard match for determination of trace concentration of the lead in the blood sample. We know that here the stripping voltammetry have a lowest detection limit. It measures the concentration up to 10⁻⁹ moles. Therefore, very small amount of metal ion, those are reversibly oxidized or reduced, can be measured by this stripping voltammetry. Students, this is all about the different types of applications of anodic stripping voltammetry. Now we discuss the sensitivity of stripping voltammetry over the polarographic method. Anodic stripping voltammetry over the polarography. Students, we know that polarography is a linear potential scan voltammetry. Performed by using a dropping mercury electrode and pool of mercury. Here, DME is working electrode and size of mercury drop is continuously changing. Therefore, that adds the charging current or a non-Faradic current in a diffusion current. And because of this, the sensitivity of this polarography is up to 10⁻⁻⁴ moles. Second case is that in polarography, only diffusion process determines the rate of reaction, and therefore we are measuring the diffusion current in polarography. Diffusion process is very slow compared to a convection process. Convection is by stirring the solution. Therefore, analyte is transported to the electrode surface only by diffusion process, and therefore this is slow. The total analyte may not be reached to the electrode surface. Therefore, it measures the concentration up to 10⁻⁻⁴ moles. In case of anodic stripping voltammetry, Here a single mercury drop is used as a working electrode. The size of working electrode is fixed. Size of working electrode is fixed. Therefore, it is free from charging current or non-magnetic current. Therefore, charging current is not associated as the size of mercury drop is fixed. Single mercury drop is sufficient to carry out the total analysis. Second thing is that concentration step is carried out at higher value of reduction potential. Higher value of reduction potential of analyte with stirring, so that analyte is quantitatively deposited onto the working electrode. Concentration step is carried out at a higher value of reduction potential with stirring, therefore total analyte is deposited onto the working electrode. And here, in a stripping step, only current, that is IP and EP, are measured for quantitative and qualitative analysis. Quantitative and qualitative analysis. Here, the detection limit for this stripping voltammetry is up to 10⁻⁹ moles. Here, we have direct result, that is IP proportional to concentration of analyte, AP proportional to the AP equal to the identification of the analyte. In case of polarography, we measure diffusion current, then E1/2. The measurement of diffusion current and measurement of half wave potential, that is requires some time. Therefore, this anodic stripping voltammetry is a faster technique of analysis compared to a polarographic technique. But one of the most important advantages of polarography is that it can be applied for those analytes which are reduced within potential range minus 2.4 volt to minus 0.4 volt versus saturated cadmium electrode, that is plus 0.4 volt. Therefore, whatever the metal ion or a analyte species that are reducible within this potential range are determined. In case of anodic stripping voltammetry, this technique is applicable for those analytes which are reversibly reduce and oxidize on working electrode. Therefore, analyte which is initially reduced, that is oxidized, and only that type of analytes are determined by a anodic stripping voltammetry. Therefore, here there should be reversible reaction for reduction and oxidation process of analyte. Then we can determine it by anodic stripping voltammetry. But here in polarography, it is not essential to oxidize that analyte back to the original form. Therefore, here the applications of polarography are little bit different than the applications of the anodic stripping voltammetry. This is all about the sensitivity of a stripping voltammetry over the polarography. Student, in today's lecture we discuss the qualitative and quantitative applications of the stripping voltammetry. In addition to this, we discuss the sensitivity of stripping voltammetry over the classical technique of polarography. With this, we stop here. Thanks for joining me. Keep learning. Happy learning.